And I just want you to remember the little bit of algebra that we had last time. So we talked about what a field is. And a field is basically some set F with two operations, addition and multiplication, and it has all the nice properties that we want these things to have. Okay, so suppose that I have a field F, and now I can define polynomials that have their coefficients in F. So let's say I have some set of variables. Let's say I have n variables, x1, x2 to xn. Then whenever I write something like this means the set of all polynomials over these variables where the coefficients come from the field F. Okay, so to be more specific, let me just give you some definitions. So I have a concept of a monomial, and a monomial is just some multiplication of my variables. Okay, so my monomial is just I from 1 to n, xi to some power, let's call it ti. And ti is a natural number, or it can also be 0. Okay, so this is what I call a monomial. So any multiplication of my variables is a monomial. Now I can say what a polynomial is. And a polynomial is basically a sum of monomials where each monomial has a coefficient coming from F. So a polynomial P is just the sum of some monomials. So let's call this M. So mi times some elements from here. So actually, let me put that element first. So ai times mi, where ai is in my field F, and mi is a monomial. Okay, and then I show the set of all of my polynomials that are of this form using this notation. So whenever I say f of x1 to xn, that basically means all polynomials that I can create using the variables x1 to xn, assuming that my coefficients come from the field F. Okay. Now, what I'm interested in is that I'm given some polynomial, and I want to see if that polynomial is 0. Okay, so, or equivalently, I can say that I'm given two different polynomials, and I want to know if they are equal. So my input is just going to be, let's say, two polynomials. Let's call them P1 and P2. And these are our polynomials with coefficients in F over variables x1 to xn. And the question that I want to answer is whether they are the same polynomials. So is P1 always equal to P2? Okay. And again, all of my calculations are done in F. So when I ask this, this is equivalent to asking, is it the case that for any valuation to the variables x1 to xn that comes from my field F, P1 of x1 to xn is equal to P2 of x1 to xn. Okay, so this problem is called polynomial identity testing, because I'm basically given two polynomials. I want to see if they're the same, right? And of course, equivalently, I can say that I'm given just one polynomial, and I want to see if that polynomial is 0. Because you just take P1 and P2 and you create P1 minus P2 and you just test whether that's 0. And that tells you whether P1 and P2 are the same. But why is this interesting? Because I want to kind of change the way that my input is given. So when I say I give you two polynomials, what do I mean by that exactly? I don't mean that I give these polynomials to you in a nice way. Instead, I just give you some function that you can call and get the values of these polynomials. Okay? So you don't actually have P1 and P2 in your input. Instead, you have two functions. Let's call them F1 and F2. Maybe I give you a library and it has these two functions. And you can basically give some value to your variables and ask F1. So what is the value of P1 given this particular value of my variables? So you can evaluate your polynomials. That's the only action that you can do with these polynomials. Okay? So you have these two polynomials. Let's say that I also know that the degree is somehow bounded. So let's say I know that the degree of P1 and the degree of P2 is at most some number d. And the only action that I can do on these polynomials is to evaluate them. I can't just go over the polynomials and ask, like, what is this particular coefficient? I don't have it in that way. I just have what we call oracle access. So I just have a function that I can call, given some particular value to each variable, and it tells me what is the value of P1 at that particular point. Okay. How would we solve a problem like this? So let's actually consider the simpler case where I'm just given one polynomial and I want to see if it's zero. So let's say my input is just one polynomial P in f of x1 to xn. And I know that the degree of P is at most some number d. And the question I have to answer is whether P is the zero polynomial. Okay. Now, this is a general problem, but for a second, let's just consider a very simple case. So let's say that my field is just the field of real numbers or rational numbers. So let's say I have a polynomial over reals, right? And let's say that I only have one variable. So I just have a polynomial that looks like this, P of x, right? One real variable x, everything is in reals. And I also know that the degree of my polynomial is at most d. And I just have to answer whether this polynomial is zero. Okay. So how can I do this? Here's the thing. If my polynomial is actually the zero polynomial, then its value is always zero, no matter what value I give to x. But if my polynomial is not the zero polynomial, then how many roots can it have? Yeah, it can have at most d roots because I know that the degree of my polynomial is at most d. So I can just try d plus 1 points, whatever points that I like. And if it was zero on all of those d plus 1 points, then I know that this polynomial is zero everywhere. But otherwise, I find the points that it's not zero, and then I say, okay, this polynomial is not zero because at this particular point, it's not zero. Okay, so the whole idea here is that if I take this value of x, there are only d different values that are roots of this polynomial. So if I want to have a randomized algorithm, I can just say, take a value for x randomly from a huge set. And then the probability that P of x is zero is going to be super small, right? So let's say I take x uniformly at random from the set 0, 1, 2 to n. Okay, what is the probability that the value of P of x is zero if P is not the zero polynomial? So in the worst case, I'm going to be super unlucky and all of my d roots are going to be in the set 0 to n, right? Okay, actually, let's say 1 to n. All of my d roots are going to be here. So even in that case, if I just take one random point here, the probability is n minus d over n that I get to a point that is not 0 for this polynomial, that is not a root of my polynomial. And of course, if I know this degree d, I can choose my n to be so large that this is as close to 1 as I like, right? So for example, put n to be 2 to the power of d. So this is the main idea. The idea is that if I have a polynomial that is actually the 0 polynomial, then no matter where I evaluate it, I'm going to get a 0. But if I have a polynomial that is non-zero, then if I evaluate it randomly over a huge set, the probability that the value of the polynomial is 0 is going to be really small. And now I explained this over real polynomials with one variable, but here we want it over polynomials who have coefficients in any field f. And instead of just one variable, I can have n variables. Okay? Now, this is what I want to prove. So this is called the Schwarz-Zippel lemma. Did I write it correctly? Yes. Okay. This is the thing. So let's say that F is a field, and let's say that P is a polynomial in F of x1 to xn. And let's say that the degree of this polynomial is d. Okay. I just take some finite set S of possible values. So let's this. And suppose S is a subset of my field, and let's say S is finite. Okay. So what I want to do is that I want to just take values for x1, x2 to xn, but for each one of my variables, I take my value uniformly at random from this finite set S. Okay, so suppose that I take the value AI uniformly at random from S, and I do this for every I from 1 to n. Now, I want to see what is the probability that P of A1, A2 to AN is 0. And I want to show that this probability is at most D over the size of S. Okay? So, is everything I'm doing clear? I have a polynomial. I know the degree of the polynomial, but I can only evaluate it. So I say I just take some finite subset of my field. If my field itself is finite, I can just take the entire field, right? And then I say for every one of my variables, I just take some value from this subset S, and I take that uniformly at random. Okay, and then I just compute the probability that P of these random values is 0. And I want to say that that probability is at most D over the size of S. And again, remember that S was this finite subset. Another way of looking at this is that if I have many variables, I'm still going to have very few roots. So I'm taking every AI from this set S, right? So how many different choices do I have? I have n variables, and for each one of them, I have S choices. So I'm trying S to the power of n different cases, right? And all I'm saying is that the ratio of the cases that actually have a root is at most this much. Okay, so I want to say that I have very few roots. Okay. How do we prove this? We can prove this by a simple induction on the number of variables n. Okay, so here's the proof. I just do. Oh, yeah, sorry. And the other thing here is that I'm assuming that my polynomial p is not 0. Right, because if my polynomial is 0, then this probability is just 1. Okay, so let's just do an induction on n. So the case of n equal to 1 is pretty obvious, right? So if I have just one variable, and if the degree of my polynomial is d, it can have at most d roots. And that's because if you have a polynomial in one variable, so something like this, and if you find some root of this polynomial, so let's say p of a is 0, then you are always able to write this polynomial as x minus a times some other polynomial. Right? This is like basic algebra, and you can do it with any field. You don't need it to be reals. So if it has more than d roots, its degree has to be more than d. Okay, so case of the base case of our induction where n is equal to 1 is pretty obvious. Now let's say that n is larger than 1, and I want to somehow get rid of this last variable in my polynomial. Okay, so I take my polynomial p, and remember, this is a polynomial over n variables. And I just separate the different monomials of p based on the degree of xn. So I write p in this format. I write that it's the sum of xn to the power of I, where I can be from 0 to at most d, right? Times some other polynomial, which I call qi. So basically, I'm factoring the terms that have xn in them. And I'm writing my polynomial p as, well, I first take all the terms that have xn to the power of d. And I just see what other polynomial qd is going to be multiplied by that. Then I take all the terms that have xn to the power of d minus 1, and so on. So I just write p in this format, where these qi's are polynomials. But the important point here is that qi's are polynomials over x1 to xn minus 1. So they don't have this last variable anymore. Okay. Now, here's the thing. If every qi is 0, the 0 polynomial, then p is also the 0 polynomial. So I can assume that there is at least one qi that is not the 0 polynomial. Okay? So I just take the largest I such that qi is not the 0 polynomial. So take largest I such that qi is not the 0 polynomial. Okay. Now, what can I say when I give some random valuation to my variables? I want to find a bound on the probability that this random valuation gives me a value of 0 for p. Okay? So here's the thing. I just check if this random valuation gives me a value of 0 for this qi. Okay? So I just take two cases. Okay? And let's say that I generate my random values for the first n minus 1 variables. So case 1 is that qi of a1 to an minus 1 is 0. Okay? And case 2 remember, I want to bound the probability that P is 0. So case 2 would be the case where P is 0. So P of A1 to AN is 0, assuming that QI was not 0. Okay, or actually A1 to AN minus 1. Do you agree that if I just find some probability bounds for 1 and 2, then I have a probability bound for my result there? So if I just say that this probability is at most some number alpha, and this probability is at most some number beta, then I can say that this probability is at most alpha plus beta. Right? Because basically what I'm doing is that I say I want the probability that P is 0. And then I say either QI is 0, and in this case I just assume P is also 0. I'm over approximating. Or QI is not 0. Oh, sorry, I forgot the not 0 part here. In which case I want the probability that P is 0. So, okay. So let's just find the bound. What is the probability that QI of A1 to AN minus 1 is equal to 0? I can just use my induction, right? So this is at most the degree of QI. What is the degree of QI? Well, it's at most D minus I, right? Because QI is getting multiplied by xn to the power of I, and the degree of the whole thing was D. So this is at most D minus I over S. How about this one? So let's say that my QI is non-zero, right? What can I say about the, or actually, let's say my QI is not 0. What can I say about the probability that P is 0? So here's the thing. I can define another polynomial. Let's call it P prime. And I just say that P prime takes only one variable. And the variable it takes is just xn. Okay? And I say P prime of xn is just P of A1 to AN minus 1, and then at the end of it, xn. Okay, so I'm assuming that I've generated random values for my first n minus 1 variables. And I'm just saying, fix those n minus 1 random values that I chose before. Now, if I fix the first n minus 1 variables, then basically my polynomial P becomes this polynomial P prime, which has only one variable. Right? And I want to say, and of course, this QI was not 0 as well. So I just want to see what is the probability that this degree 1, that this polynomial on one variable is 0. Okay, but what is the degree of this polynomial? So it only has xn in it, right? And I chose I here to be the largest I, such that QI is not 0. So the degree of this polynomial is going to be at most I. And the probability that P is 0 is the same as the probability that P prime is 0, because I already have this assumption here. Right? So this probability is just going to be the probability that P prime of AN is 0. And this probability is at most what? So it has degree I, and I can just put I here instead of D. So this is at most I over S. Okay. D minus I over S, I over S. You sum them up, you get D over S. Okay. So yeah, that's it. That's the proof of the Schwarz-Zippel lemma. Okay. But how does this help us? Now that I have this lemma, how do I solve this problem? Well, the degree of my polynomial is fixed, right? I just need to choose my set S to be large enough. Okay. Now, can I do that? Well, it depends on how big this field is, right? But just assume for a second that this field is either infinite or big enough for all of our use cases. If this field is big enough, then I can choose an S here that is as large as I like. And then D over S can get as small as I like. So if I just choose a large enough set S, then in order to answer this question with high probability, correctly with high probability, I can just evaluate my polynomial once over one random valuation of the variables, right? And if the value was 0, I say with high probability, the polynomial itself is 0. If the value was not 0, I say with high probability, it's the polynomial. I say I'm completely sure that the polynomial is not 0, right? Because I have a value that is not 0. Okay, nice. And of course, if you have some limitations, if you cannot make S as large as you want, you can just repeat the algorithm, right? As long as this value here, D over the size of S, as long as this is less than 1, you can just take the algorithm and repeat it as many times as you want. We've seen this in the randomized algorithms module, and you can just decrease the probability as much as you want. Okay, nice. So what is the runtime here? Well, basically, I'm doing one evaluation. I'm generating n random numbers. So my total runtime is n times the time it takes to generate a random number plus the time it takes to evaluate the polynomial, right? And I can't give you any better analysis because it really depends on how you generate random numbers and how you have access to the polynomial. So we just assume that we can evaluate it. We don't know how much time it takes, right? But usually we assume that we can generate random numbers in constant time. So if we can generate random numbers in constant time, it's just n plus whatever time it takes to evaluate this polynomial. Okay. So let's actually see a use case of this. And the use case I want to talk about is perfect bipartite matching. So let's say that I just give you a bipartite graph, and let's say that both parts of this graph have the same number of vertices. So my input is just a graph G, let's say with n vertices. And additionally, I also have a bipartition of G. So I have sets L and R that are both subsets of V. And I want to say that they have the same size, such that LR is a bipartition. So every edge goes from L to R. Every edge has one endpoint in L and one endpoint in R. So L disjoint union R is V. And yeah, I'm too lazy to write it formally. Every edge has one endpoint in L, one endpoint in R. So I have L I have R. I have these edges. Now, what is the question? The question is whether this graph has a perfect matching. So does G have a perfect matching? Okay, what is a perfect matching? A perfect matching is basically a set of n over 2 edges so that no two of them have to share any endpoint. So I'm just matching each one of the vertices on the left to one of the vertices on the right, and exactly one. And there is an edge between every vertex and its pair. Okay. Now, you should know how to solve this using maximum flow and things like that. But I want to give you a randomized algorithm that actually uses polynomial identity checking. Okay. So I hope that some of you have taken linear algebra before, but if not, I'm just going to define everything that I need. So Sn is basically the set of all permutations over the numbers 1 to n. Okay, so this is permutations over 1 to 2. Okay, now I want you to just consider the adjacency matrix of this graph. So let's say that A is the adjacency matrix of G. Now we can compute what we call the permanent of A. And this is something that people really care about in linear algebra, but I just care about its definition. I don't care about its other use cases. So the permanent of A is basically the sum over every possible permutation of the product of AI sigma I. And I goes from 1 to n. Okay, so I take every possible permutation of my vertices, and I say for every vertex I just look if I is a neighbor of sigma I. Okay, and if they are neighbors, then this value is 1, otherwise it's 0. I multiply all of that together, that gives me a value for this particular permutation. And then I just sum it up over all of my permutations. And that's called the permanent of A. Now, why do I care about this? Because you can see that there is a relationship between this value and whether my graph G has a perfect matching. So you can think of a perfect matching as some sort of a permutation over the vertices. So you can think that I'm matching vertex I with vertex sigma I, which is like the ith vertex in the permutation, right? And then it's a perfect matching if every vertex has a match. So if A of I sigma I is 1 for every possible value of I. So in other words, if I have some permutation of my vertices that gives me a perfect matching, then this part here, the contribution of that permutation is going to be 1. Otherwise, this part is going to be 0. Okay. In other words, the permanent of A is basically equal to the number of perfect matchings of A. So it's not only telling me whether I have a perfect matching or not, it's actually counting them. So this is equal to number of perfect matchings. Great. So if I have a graph, I just take its adjacency matrix and I just compute the permanent of the adjacency matrix. Unfortunately, this is an extremely hard problem. We don't have a polynomial time algorithm for computing the permanent, as you can imagine. Like, if we had a polynomial time algorithm to count perfect matchings, it would be a perfect world, but we don't have that. Okay, so what do we actually have? So there is this other parameter that we actually know how to compute, and that's the determinant of a matrix. Okay, so what is the determinant of a matrix A? I'm sure you've seen it before. You've definitely seen it for small matrices. But in general, what is the definition? The definition is actually very similar to this one. It's just the sum over every possible permutation of the sign of that permutation times this same thing. I from 1 to n, ai sigma. And maybe I should put a comma here as well. Okay. So what is the sign of a permutation? Again, this is something that you should have seen in algebra or linear algebra. If I take any permutation, I can just write it as a series of swaps, where I take two elements and swap their position. And if I can write a permutation as an odd number of swaps, then I say that permutation is an odd permutation. And if I can do it as as a combination of an even number of swaps, then I say that permutation is an even permutation. And this sign here is basically like 1 if it's even, or -1 if it's odd, or maybe the other way around. Yeah, it doesn't really matter because the whole thing gets multiplied by -1. Okay, so that's what the determinant is. So this sign is either 1 or -1. But we don't really care about that. What we care about is that we have fast algorithms to compute the determinant of a matrix. And actually, like, again, in linear algebra, you should have seen this. There is this thing called the LU decomposition, which computes the determinant of a matrix in cubic time. So if you have an n by n matrix, you can compute its determinant in O n cube. But as usual with matrices, there is an algorithm that is actually n omega. Okay, but anyway, what we care about is that this determinant is easy to compute in polynomial time, whereas this permanent, which is very similar to the determinant, it just doesn't have that sign there, is basically impossible to compute. It takes exponential time. Okay, but this one counts the number of perfect matchings. This one doesn't. So I want to somehow create a polynomial that uses this determinant, and I want to say that that polynomial is 0 if and only if I don't have a perfect matching. Okay, now how do I create a polynomial like that? This is the really nice part. So I just create a lot of variables. Remember, my polynomials were over n variables before. Now I actually create n squared variables. So I say for every 2 vertices, I and j, I create a variable which is called xij. Okay, and then I'm going to define a polynomial over all of these xij variables. Now, how do I do that? Well, I just say, let's take my matrix A and let's change it to a different matrix that I call A tilde. And I say, I take the ij's entry and I look at my original adjacency matrix. if in the original adjacency matrix I had a 0 there, I put a 0 here as well. But if in the original adjacency matrix I had a 1, I put this variable here. I say xij. Okay. So basically, the only thing I'm doing is that I'm taking my adjacency matrix, and whenever I have a 1 in the adjacency matrix, I'm just putting a variable xij in place of that y. Okay. Now, what happens if I take the determinant of a tilde? So here's the thing. We looked into this part, and we said that this part is 0 if the permutation sigma doesn't give us a perfect matching. And it's 1 if the permutation sigma does give us a perfect matching. Now, this part here and here are basically the same, right? But our problem is that maybe, let's say I have 2 perfect matchings, and I get 2 1s here, and then one of them gets multiplied by -1 and cancels the other one, right? So I want to avoid the cancellation, basically. So what I'm doing here is that instead of just using numbers, just using 0 and 1, I'm putting these variables into my adjacency matrix. So now the cancellation doesn't happen because they're different monomials. So if I take this determinant, let me just write it again. It's sum over every possible permutation of the sign of that permutation times the multiplication of a tilde I sigma I, where I goes from 1 to n. Now, look at this part here, right? So if I don't have a perfect matching that corresponds to this particular permutation, then one of these I sigma i's will be 0. And so this whole thing would be 0, right? But otherwise, this thing would just be a multiplication of some xij's, right? But it's different from any other multiplication of xij's. So even having this sign, even having the +1 or -1 here, would not cancel these terms out. Okay, so great. Now I have this extra ability that instead of looking at the permanent, I can look at the determinant. And I can say that this determinant of a tilde is the 0 polynomial if and only if G has, or okay, it's not the 0 polynomial if and only if G has a perfect matching. Okay. But yeah, as you see, we have a problem here. And our problem is that this is a polynomial now. Because instead of just having 0s and 1s in my matrix, I have 0 and I have these variables. So when I just compute, let's say, this determinant according to definition, I get a polynomial. And I cannot just naively and symbolically compute this determinant. Because if I try to do that, my polynomial might get really large, right? So I could compute determinants in polynomial time when all of my entries were just numbers. Because if you multiply 2 numbers, you just get another number. If you add 2 numbers, you just get another number. But when you have polynomials, if you multiply 2 polynomials, your degree goes up and you need more space to save the resulting polynomial. Okay, so I can't just compute this. But I can evaluate it, right? So if I give you some values for these xij's, then it's just finding the determinant of a normal matrix, and we can do that in polynomial time. So now I have this polynomial, and I want to see whether this polynomial is equivalent to 0, it's equal to 0 at every point. and I can evaluate it in n cubed time. So I just use my previous algorithm for polynomial identity checking, and I just check whether this polynomial is equal to 0 or not. Of course, in order to do that, I have to know like the degree of this polynomial, but that's not too hard, right? Because this is just the sum of something, and then I have to just find the degree of these monomials. And the degree of each of these monomials is at most n. So I do have a bound on the degree of my polynomial. Now, another nice point here, what field is this polynomial in? So I talked about this idea that the coefficients of my polynomial can come from any field f, right? But what field is this polynomial defined in? Well, honestly, I just have 0 and I have my variables. So I can just use any field that I like. I don't have to use the field of real numbers or anything like that. So you can just use the field of numbers modulo p, like integers modulo p. And as long as you choose your prime number p large enough so that your field is big enough so that you can do polynomial identity testing, then you can check whether this polynomial is equal to 0. Okay, great. So let's see if we can apply the same idea to a problem that we have seen many times already. And that's the problem of k-path parameterized by the number k. Okay. So our problem is k-path parameterized by k. And remember, the input is just the graph. And the question is whether this graph has a simple path that has k different vertices in it. And we've already seen some solutions using color coding. We saw a solution that took, what was it? Yeah, it took 2e to the power of k times some function, some polynomial function of n. This was the naive, no, this was the color coding where we were considering that we just want to have different colors in every path. But there was also this algorithm where we said we want to have exactly colors 1 to k in that same order. And that gave us something like k factorial times n to the power of c. So now I want to get an algorithm that has better runtime than this. And of course, in all of these cases, I want to get the right answer with high probability. Okay. Again, our tool is just this randomized algorithm that we have that takes a polynomial and tells us whether that polynomial is 0 or not. Okay. So first, I need a very simple lemma. And my lemma is this: for every integer k, for every positive integer k, there is a field that has 2 to the power of k elements. There is a field f such that the size of f is exactly 2 to the power of k. Okay. And additionally, I want to have one more property in this f, and it's that the field has characteristic 2, which means 1 plus 1 is equal to 0 in this field. Now, to understand the algorithm, you just need to know that such a field exists. But actually, if you're interested in knowing how we can create a field like this, we can just take the field F2, and F2 is just numbers modulo 2, 0 and 1. Okay? And then we can take all the polynomials that have their coefficients in F2. So let's say I take F2, let's say with just one variable. Okay? But this set is not a field itself. Like F2 is a field, but if I have all polynomials in a single variable x that have coefficients 0 and 1, yeah, I can add, I can subtract, I can multiply, I cannot divide, right? So I have the polynomial 1, but I don't have multiplicative inverses. But the situation is very similar to natural numbers. So if you consider natural numbers, they don't give you a field either. Like there is no number that can get multiplied by 2 and gives you 1 in natural numbers. But when we take natural numbers modulo some prime number p, then we get a field. So here we can do the same thing. We can take all the polynomials, but we can take them modulo some prime polynomial. So this thing modulo some polynomial q, where this q has to be prime in a sense, and the sense that it's prime is that it's irreducible. So you cannot write q as a multiplication of two other polynomials that have degree larger than 0. Okay, so again, you don't need to understand this, just know that a field like this exists. Okay, this is the construction. You can look into any algebra book for proofs that this works. Okay, and also another point here is that since I'm basically working with polynomials that have k different coefficients, I can think of each one of my polynomials as basically a bit vector with k different bits. So each one of the operations in this field takes O some polynomial of k for every operation. So I just want this so that I can tell, so that I can say that in this field I can use the operations like multiplication and addition and so on in constant time or in very small time, depending on k. Okay, so why do I want a field like this? Because basically, if you remember what I was doing with the determinant, I was trying to avoid cancellation. But sometimes I want to make cancellation happen. I want to make sure that I create some polynomial and then some parts of it, some monomials cancel other monomials, let's say. Okay. Now, why do I want this? You'll see very soon. So, but the really important point here is that I want the characteristic of my field to be 2. So I want to have 1 plus 1 equals to 0. So if I have the same term twice, I basically don't have it. And basically, if 1 plus 1 is 0, then a plus a is 0 for every a, because a plus a is just a times 1 plus 1, which would be a times 0, which would be 0. Okay? So that's why I need this part. Okay. Let's go back to our problem. I want to say that I have a graph G and I want to see if I have a k-pass. So let's try creating different polynomials. Now, what is my goal? My goal is to create some polynomial p such that p is not the 0 polynomial if and only if my graph G has a k-pass. This is my goal. Because if I can do this, and if I can then evaluate my polynomial p, then I can just use my randomized algorithm for polynomial identity testing, and I can see if this graph has a k-pass or not. But of course, the hard part is coming up with this polynomial p. So here's the thing. Let's just take the idea that we had from the previous problem, from using permanent, and let's say that my P is just going to be the sum for every possible path of length k. So over every path, let's call it, well, what should I call my path? Let's call that path, okay, let's call it this P of size k, so with k vertices. And then let's say that I want to have some monomial that is defined only based on this path. Right? I haven't defined what kind of monomial I want to put here. So if I have such a thing, then of course, as long as I have even one path, then this thing would be non-zero, assuming that these monomials don't cancel each other, right? And then I can be sure that I have a k-path. But the problem is that this is not going to really work, because if I can compute this P, I'm basically summing over all paths of size k. And if I had all paths of size k, I would know if I have a path of size k, right? That's very trivial. But there is something else that is much easier. So we can, for example, count the number of walks with k vertices instead of paths. So, and by walk, I mean like a non-simple path, a path that can go back to the same vertex. Okay? So, yeah, this idea doesn't work. But what happens if I say I want the sum over all walks W with k vertices? Okay? And then I want to have some monomial of W. Okay? Now, this is more doable because I can at least count the number of walks with k vertices in my graph. It's just matrix multiplication. Right? But here's the smart part. I want to define these monomials in a way that they cancel out if this walk is not a path, so that I basically get the sum over all of my paths on. Okay? But that's not so easy. So instead of a monomial, I'm actually going to use a polynomial for every path. And yeah, I'm just going to give you the answer. But basically, the way they came up with this answer was that they were just trying different polynomials to see what works. Okay, so here's the answer. First of all, let's say what variables I have. So variables. I define two types of variables. First of all, for every edge E, I add a variable that is x sub E. Okay? So again, I'm creating a polynomial over a lot of variables, so I'm first just defining what my variables are. And then I'm going to also use coloring. So let's just assume that I'm going to color my graph with k colors again. So I say that for every vertex V and every color, let's call that color C, and let's say that it's between 1 to k. I define a variable, and let's call that variable, because that one was x, so this one is y. And let's say it's y of V and C. Okay, so how many variables do I have in total? I have one variable for every edge. So I have m variables here. And here I have k variables for every vertex. So I have n times k variables here. So the total number of my variables is m plus n times k. Now, here's the important part. How do I define my polynomial p? So remember, what I want here is to make sure that anything that I add into my polynomial that is for walks that are not paths is going to cancel out. Okay? So this is the definition. I take the sum over all k walks W. So let's say I take every walk with k vertices, which is W, and let's say in it I have W1 to WK. These are the vertices. And then I take every possible coloring of this walk. Okay? So I take the sum over all bijective functions, and I'm going to call that function C, that map W or map 1 to K to 1 to K. Okay? So the idea here is that I'm coloring the ice vertex in my walk with color CI. Okay? And of course, I want my walk to have different colors. So I take this sum, and then now I have to put a monomial here. So what is my monomial? My monomial is just the multiplication of x of every wi and wi plus 1 times the multiplication of y, out of space, of wi and c of y. Okay. This is the polynomial we're going to work with. Now, you'll see the intuition in a minute, but what am I doing? I'm taking every possible walk of length k that has vertices w1 to wk. And then I'm taking every possible coloring of that walk. Okay, every possible way that I can map each one of these vertices or each one of their indices to a color between 1 and k. And I want to do that in a way that they get different colors. So they have to be bijective. This C has to be bijective. And now, what am I computing as my monomial? I'm just taking the variables corresponding to all the edges in my walk. So remember, the x variables were the ones that corresponded to edges, and I had one x variable for each one of my edges. So there is an edge between wi and wi plus 1. I can take x of that edge. I'm multiplying all of these together. And then for every vertex and every color, I had another variable, which was the y of that vertex and that color. And I'm multiplying all of these two. So I'm multiplying everything here, and then I'm summing up over all the walks and all the colors. Okay. Now, why did I define a weird polynomial like this? Because I want to say that if this walk W is not a simple path, then all of these parts that correspond to W will cancel each other out. Okay? So that the sum that I get is actually just going to be the sum over all paths. That's what I want to say. So this is my lemma. If W is a non-simple walk, so, or if W is not a path, then the contribution of W to this sum is going to be 0. Okay, then, okay, what is the contribution of W to this sum? It's just this part. Okay, so then that part, which I'm not going to write again, is going to be 0. Now, why is that? Oh, and I'm assuming that I'm using the fields that I just told you about. So adding some element to itself would just give me 0. The characteristic is 2. Okay. So let's just look at my VOC W that is not a path. So I start from somewhere, I go somewhere else, and then at some point I go back, because this is not a simple walk, this is not a simple path, so I see this vertex again, and then I go here. Okay? Now, just take the ordering. So this is, let's say, the order in which I saw the vertices in this walk. So this is going to be W1, this is W2, this is W3, W4. I come back, so this is also W5, W6, W7. Okay? Now, just consider any coloring. Let's consider the first possible coloring, which just gives the same color. So let's say I gave color 1 here, color 2, color 3, color 4. I come back, I again give color 5, color 6, and color 7. Okay? Now, what is the monomial corresponding to this? It's just that, well, this part is only using the edges, right? So I just get, let's say, 1, 2, 3, 4, 5, 6. I have 6 edges. Let's call them E1 to E6, right? I just take x of E1 times x of E2, so on, to x of E6, right? Then I have this part, which is basically y of W1, 1, y of W2, 2, and so on, and y of W7, 7. So this is the monomial corresponding to this particular coloring. Okay? But can I find a different, let's say, a path and a different coloring that, can I find a different walk and a different coloring that gives me this exact same monomial? Right? Yes, because you see, my walk was this one, right? But instead of, and what was my coloring? I was giving color 1 here, then I was giving color 2 here. And then the next time that I was coming back, I was giving color 5. So I can just swap the ordering of the colors. I can say I take another, I take the same walk, but a different coloring function. And the only thing that it does is that it swaps 2 and 5. So I start here, I give this one color 1. I go here, I give it color 5 this time. And then I go all the way, and when I come back, I give color 2 the second time. Right? That's going to give me exactly the same monomial. So in this whole sum that I have, this monomial is appearing 2 times. And I'm using a field whose characteristic was 2. So anything added to itself is 0. So if I add this monomial 2 times, I'm just getting 0. And you can try this for every possible monomial. So you can say, I take any W that is a walk but not a path, and you can just find pairs of monomials that match exactly like this with this construction. And then this tells you that the contribution of W is basically 0, because it has a bunch of pairs of equal monomials that are getting added to each other. So if W is not a path, then this part, the contribution of W to my polynomial, is just 0. Okay, so my polynomial P is now equal to the same polynomial, except that instead of taking K walks, I'm taking K paths. And again, the same thing, I'm too lazy to write it again. right? Because the walks that were not paths are not contributing anything to the polynomial. But this is not enough. I have to show that the paths actually do contribute something, because what if this polynomial is just always 0? Right? So my first point here was that if I take a walk W that is not a path, it doesn't contribute anything. But then I want to say that if I have a walk W that is a path, then it contributes something, and that thing is not going to be canceled by the contribution of the other paths. Right? But that's also quite easy. So if W is a path, then this thing that W has is not 0. And also, I just say that it has completely different monomials from every other path. So here's the thing. Let's say that I have a path of length k. So W1, W2, so on to WK. What are the monomials that this path contributes? Okay, let's just write it. So it's just x of W1, W2 times x of W2, W3 times so on to x of WK minus 1, WK. Right? These are the variables that it contributes because of its edges. Now, I can take any possible coloring. And so for every coloring, I will also have times y of W1 and the first color. Let's call it C1. Y of W2 and the second color, and so on. But here's the thing. This is the only path that has this particular set of edges. So when I'm talking about paths, if I just give you the set of edges, I've given you the path uniquely. Right? So this thing, this part is completely unique. It makes it unique so that this particular monomial is not going to be created by any other path. But is the same monomial going to be created more than once by the same path? No, because this part is again unique for every possible coloring. So every monomial that a path creates in this sum is going to remain there. It's created exactly once. It's not going to get canceled. Okay. So based on this, this particular P has the property that was my goal. So if I just say that P is this, then P is a non-zero polynomial if and only if G has a k-path. So if I can evaluate P, I can say with a good probability whether G has a k-path or not. But the funny thing about this algorithm is that I don't actually find the k-path. It's just that I evaluate this polynomial, and if it's non-zero, I say that, yeah, with very high probability, I do have a k-path, but I don't know where it is. Okay? So the final piece of this puzzle is how to evaluate this polynomial. Because again, if you consider this, if I just do it naively, it's going to take exponential time. I don't want to spend exponential time. I just want to say that if I give you some values for the variables x and y, can you evaluate this polynomial using that given values really fast? And of course, I'm going to choose those values randomly and then use the Schwarz-Zippel lemma. Okay. So how do you evaluate this? If I give you the values of x and y variables, how do you evaluate this?
Non-simple path said that if it's non-simple walks, then you make this out eventually to be 0. But because Although
So the same monomial always gets added twice, right?
always twice, would that be three?
Well, it's always an even number of times. You can try it. Like if it comes back like 3 times, then you will have 3 factorial different ways of going through this. So the number is always going to remain even. So if you have a path that goes back to itself I times, you can rewrite it I factorial different ways. Yeah. Okay. So how do we evaluate this? So maybe I can just do a dynamic programming. And this is the simplest thing that I can do. So just imagine the algorithm that we have for just counting how many walks of k vertices, how many k walks we have. It's basically a dynamic programming. We can maybe do a similar dynamic programming here. So I can do this. I can take the dynamic programming variable to have these things. So let's say it has v, it has k prime, and it has some function c. So this function, it's just a bijective function that maps 1 to k to 1 to k. This k prime is a number that is at most k, and this v is just a vertex. Okay, so I can say find this whole sum if we fix this particular c, and if instead of having paths of length k, I have paths of length k prime, and if I want my path to end at vertex v. Okay, so this same sum, except that here I say that wk has to be v, and here I say that this c is the one that is fixed, so I'm not summing over every c, and that's it. And oh, this k is also now k prime. So I compute this sum, but for shorter paths. Now, if I can compute this, then I can just do dynamic programming and compute my actual p. And again, at this point, I'm just evaluating p. So I'm assuming that I have values for these x and y variables. I'm not doing any kind of like symbolic computation or anything like that. I'm not keeping these variables. Okay, but how much time would it take if I do a dynamic programming like this? So for my vertex v, I have n different choices. For this k prime, I have k different choices. For c, the number of choices is the number of bijective functions from 1 to k to 1 to k, which is k factorial. So this is the runtime that I get, right? Times some polynomial that I need for actually computing these things. And this is terrible. This is as bad as the first color coding idea that we had. It has k factorial in there. So maybe we can do a better dynamic programming. So let me remove this. Okay. So instead of fixing the coloring, maybe I can just say which subset of colors I want to be able to use. Okay. So I can now define my dp in a similar manner. So v k prime, but now I have a big set C, which is the set of all the colors that are allowed. Okay. And I say that this dp is going to be the sum. So I'm just writing from here. I want to have k walks in the end, but here I want to have k prime walks. Okay. So sum of k prime walks w1 to wk prime, and I want my walk to end at vertex v. So such that wk prime is v. Okay, now I do the sum over the bijective functions, but now I have only k prime variables here. And instead of using all the colors, I want to only use the colors that are in this set C. Okay, so instead of having bijective functions, I have one-to-one functions. And again, I have the same function C, but now it maps 1 to K prime to, well, this set C. These are all the available colors. And then the rest of it is exactly the same. So I just take X of Wi plus 1, where I goes from 1 to K prime minus 1 times this thing, and Y of Wi C of I. And this time I goes from 1 to K. Okay? So again, forget about whatever I have here. I'm just thinking about the sums. I want the sum of this thing, whatever it is, over all vox of length K, and over all colorings that use all the colors, right? So I say, first of all, I do it separately for every end vertex. So for every vertex V, I say I only take those vox that end at the vertex V, because then I can sum up over all of my vertices. Then I say my lengths in my DP, instead of having the final lengths that I want, which was K, let's have K prime. And then finally, for the colors, I say instead of using all the colors, let's use this subset of colors. And I define my DP like this. Okay. Now, we're out of time. You can figure out how to compute this DP. Actually, it's pretty easy to compute each one of these DP variables in polynomial time. But how many DP variables do we have? So I have n different vertices. I have k different values for k prime. And for C, I can have 2 to the power of k different subsets of colors. So my overall runtime is just going to be O n times k times 2 to the power of k times some polynomial in it. Okay, which is FBT, and it's actually 2 to the power of k, which is better than all of the color codings that we saw. Because the best color coding algorithm took 2e to the power of k. This is just 2 to the power of k. But again, the important point here is that I'm taking this p and I'm evaluating it in that particular finite field that I had, where the characteristic was 2. So adding any 2 elements would just give me 0. And that's it for this session.